Hey, I'm back. I don't even know how this is going to work. I had an important phone call. Somebody actually had crashed into my daughter's car when she was driving it, and it had to get fixed. And that was the body shop. And she's fine, and the other driver's fine. It was very lucky that nobody had a problem, and it was the other guy's fault. And so their insurance company's paying for the total damage, which is even better. But I'm just glad, of course, that my daughter and the other person is healthy. If you drive, you have to be very, very careful, right? Driving is a privilege, and it's not always you. Sometimes it's crazy other people that can create problems. You have to always be defensive. So that was the body shop. I had to talk to them. They wanted to know some stuff. And so it's all good. I'm back. I hope this all worked out. So the original conditions of pressure and volume exist because I have a gas. This is my gas. This is my sample of gas. I could have a different sample if I blow up a different balloon, bigger balloon, more pressure, more volume, whatever. But my sample of gas starts with some constant conditions, pressure and volume. And if I change one, the other one changes inversely. It changes. And when you plot all of the points on a graph where my balloon, as the volume gets bigger and the pressure goes down, or when the volume gets small and the pressure goes up, my graph of my gas would look in this curvilicious kind of a way. And each point on the graph, every point on the whole curve, each point would be equal to every other point because pressure times volume, 1, equals pressure times volume 2, or pressure times volume 3, or pressure times volume 4, or as million points, as many points as you want. Because the gas sample is a gas sample. It exists, it's real, it's one set of data, and as you switch one, the other switches inversely. Now, if we multiply pressure times volume, now my gas, I don't know what's going on here. It's 1.20 on top and 1.30 on the bottom. Let's see what the actual number is. It apparently is 1.30. So let me fix this. I don't know how this happens. Some little gremlin gets into my computer sometimes and wrecks my slides. So my starting condition of 1.30 atmospheres and 350 mLs, when I multiply those two things together, it equals 455, and the unit would be atmospheres times milliliters, which is total wacko unit. But my sample, I measured in atmospheres in milliliters, so that's what my unit is. This is called the gas constant for my gas. This gas has that constant. Now, if you blew up a balloon, the odds of you getting exactly 1.30 atmospheres and 350 mLs is pretty remote, really. I mean, you'd have to do some fancy blowing up a balloon to make it that perfect. But the thing is, my sample has this. Now, if I change the pressure or change the volume, pressure times volume is always going to equal itself. So watch what happens. If I have P2V2, pressure times volume up there, higher pressure, lower volume, has to equal 455 atmosphere mLs. P3V3 at the bottom. Look, I have very low pressure. I got much bigger volume. It's also got to equal 455 atmosphere mLs. Every single point on this graph, the graph of this sample, my sample, every point, pressure times volume equals every other point, pressure times volume. And for this sample, it happens to be 455 atmosphere milliliters. That's my sample for my gas. Every gas sample has its own gas constant. It's sort of temporary. It's for that sample. When I pop the balloon, I lose my pressure and volume. I don't really have a sample anymore, and so I won't really have a constant. Every gas has its own constant because it has a pressure times a volume. Now, let's make a new balloon. You give me your balloon. Put a balloon in your head. Make it a different color. It's a blue balloon, and it's only got nitrogen in it. And it's 3.75 liters, so it's pretty big. And the pressure now is in different unit, but it's 125 kPa. So you blow it up, it's a little hard, not like a basketball, but it's a little higher than normal. 101.3 kPa is normal. What's the gas constant for your gas? Because yours is different than mine. You're even going to have different units. So how do we do this? the pressure times the volume equals a constant. Now for your gas, in the blue balloon that you just have in your head, the pressure is 125 kPa and the volume is 3.75 liters. Multiply them together, you get 469. And the unit's weird, different than mine too, because you used kPa's times liters. So it's kPa times liter, weird unit. It's okay, we like weird units. Your gas has a gas constant. My gas sample has a gas constant. Every gas has a gas sample constant. Every sample is different and has different pressure and different volume, and you could use the same, kind of balloon with different units. All right, what if we can change the conditions of your blue balloon? See, I wrote up in black there, the constant is 469 kilopascals times liters. What if we change the conditions of your nitrogen gas sample all the way up to 9.75 liters? What if we make it really big? What's going to be the pressure? What's going to be the pressure? So let's see what we got. Slideshow from current slide. For your gas sample, pressure times volume is a constant. Pressure times volume equals 469 kPa. The pressure, my goodness, this question's a mess, but the pressure here is going to be down to 48 kPa. That makes sense. When the volume goes up, the pressure goes down. What happens to the pressure? I don't know. Who typed this slide? Pressure times volume is a constant. And for your gas, we have a constant. Pressure times the new volume equals the same constant, so we can divide both sides by 9.75 liters, and the answer pops out. We get this lower pressure. Makes perfect sense because they're inversely proportional. Now, it's called Boyle's Law, and I leave this because I really like that font. I really like that fancy old font, Boyle's Law. We talked about this already, but here it is again. The pressure times the volume for a gas sample is always equal to a constant, which means if you change the pressure and volume, it's equal to itself. So instead of P times V equals a constant, we can also say the starting pressure times volume is equal to the new pressure times the new volume. This is part of the combined gas law. It runs across the top, and this is the part that's inversely proportional. Now, we're going to do the same math problem two different ways. We're going to do the math in kilopascals. We're going to do the math in atmospheres. You're going to see to make sure this makes perfect sense. It says at constant temperature, when we have constant temperature, we can just cancel the temperatures in the formula. We don't even know what the temperature is. So we're going to use P1 V1 equals P2 V2. Now, sample of neon gas is at standard pressure. Standard pressure, what are we going to use? Let's look at table A. Standard pressure has two units, kPa or atmospheres. On the left in black, we're going to do it in kPa, and then we're going to do it on the right in atmospheres. Standard pressure and 45.8 liters. If you double the pressure, we can figure out what double the pressure is. What's the new volume? All right, let's see, in kPa. This is how we're going to do it. We write the formula both times, but we'll work on the black side first. We're going to do it in kPa. Standard pressure is 101.3 kPa, and the balloon is 45.8 liters. If we double the pressure, that means 2 times that, the pressure goes up to 202.6 kPa. What's the new volume? Well, we got to get the volume by itself, so we're going to divide both sides by 202.6 kPa. The kPa's are going to cancel, which is good because the unit that's left is going to be liters. So to do this math problem, we got to do 101.3 times 45.8 equals, and I get this big number, like 44,600. And then we're going to divide it by 202.6, and that's going to equal 22.9, and the unit left is liters. So if we do this gas problem in kPa, pressure times volume equals pressure 2 times volume 2. If we have starting conditions and double the pressure, the volume goes down to 22.9 liters. What if we do it? What if you didn't pick kPa? What if you picked atmospheres? Is that okay? Yeah, it is. Look. In this case, in red, we're going to put in 1 atmosphere times the volume, because that's standard pressure, and we double the pressure. Well, what's the pressure? Double 1 is 2. You double it up to 2 atmospheres, and then you get V2 by itself. How do we figure this out? We're going to divide both sides by 2 atmospheres, and we get V2 by itself. To do this, it's going to be, well, 1 times 45.8. That's just 45.8. And then we divide it by 2, and look at that. We get 22.9 again. It doesn't matter what units you use as long as they're consistent on both sides of the equal sign. For volume, any units, as long as they're consistent. For pressure, any units, as long as they're consistent. For temperature, gotta use Kelvin. Gotta use Kelvin. All right, you have a really thick rubber balloon and it's big. It's got 19.8 liters of oxygen gas. Doesn't matter what gas, all gases work the same. The oxygen just makes it like you could believe it. The pressure inside is 1.73 atmospheres, so it's a little firm. You sit on it and you squash it and it squishes. Instead of being 19.8 liters, you squash it down to 14.6 liters. What's the new pressure inside? Well, you need to see, this is an easy math problem. This is a pressure and volume problem. Nothing about temperature, so temperature must be constant. It's a gas problem. When it's a gas problem, we're going to use the combined gas law. But we have constant temperature, so we can just write this formula. The original pressure and volume multiplied equals the new pressure and volume multiplied. So what is the original pressure? 1.73 atmospheres. What's the original volume? 19.8 liters. What is the new pressure? That's the unknown. What is the new pressure? That's the question in blue. That's what we're looking for. The new volume goes down to 14.6. So we plug the numbers in like this, right? And in order to get P2, the unknown, by itself, we have to divide both sides by 14.6 liters. And that's what it looks like. We have the starting pressure and starting volume divided by the second volume. And we can solve for P2. The liters are going to cancel. The math is going to come out in atmospheres. Listen to me. You don't want to do this. I don't want to do this. Nobody wants to do this. But what's amazing is in the 1680s or 1690s, Mr. Boyle came up with this. He said, when you take a sample of a gas, one sample, if you increase the pressure, the volume goes down. And if you increase the volume, the pressure goes down. And it's perfect. And every gas is the same. It could be oxygen, it could be neon, it could be carbon dioxide. Gases are gases are gases. And the gas laws are perfect. And there's always a lot of words. But there's one formula, and sometimes when you have something easy like constant temperature, you make a little formula out of it, and then the numbers work perfectly. Use your units, and you can't get this stuff wrong. Now, what are the variables that we use to measure and talk about gases? Okay, the first one, of course, is pressure. And we can use any units. We can have kilopascals or atmospheres, millimeters of mercury if you want to be old-fashioned, old school like me, or pounds per square inch if you want to be American. In Europe, they don't even do PSI, right? It's like, what are you, dumb? What are you, American? We don't use PSI over here. But you could. As long as the units are the same on both sides, they'll cancel, or you'll get an answer with that unit. And if you need it, if you're doing a work in kPa, but the question is, and now what is the answer in PSI? Well, at the end, you do a conversion. But as long as the units are consistent, these are all the units we can use for pressure. For volume, you could use anything. You use liters normally, or milliliters or centimeters cubed, which are the same size, but your units have to be consistent. I suppose you could use cubic meters of gas or cubic feet of gas. I mean, anything. You could use a balloon full. How many balloonfuls? But we generally use liters, milliliters, or centimeters cubed. The third variable is the temperature, which always is in Kelvin. You can't ever have a 0 degrees. And today, well, it's warming up maybe a little. It's probably still in the negatives. You can't have a negative number in the denominator, and you certainly can't have a 0 in the denominator, ever. So we have to use what's called the absolute temperature scale. You have to use Kelvin. And guess what? With the combined gas law, right in this space over here, you might want to write something. Let me get my pen. Use Kelvin. So right next to the combined gas law, you might want to write that. Use Kelvin. And if you're really kind of goofball, put an exclamation point. We only use Kelvin. And the last unit that we're going to use for gases, are we ready for this? Moles. They're back. This is kind of like a horror movie. You thought it was over, and now they're back. Just when you thought you were out of it, they drag you back in. It's going to be great. All right? 4 variables use gas, all right, to measure gases. You talk about the pressure, the volume, the temperature, and also, of course, moles. And once you have moles, you know, you can do all kinds of conversions. It's going to get all intertwined and interconnected. It's going to be great. It's going to be like a bowl of linguine and clam sauce, all intertangled and no beginning and no end. It's just really cool. It's all chemistry. All right, look what I got. A couple more pictures. Let's imagine when we put a balloon in hot water. See my balloon? What if we put this balloon in a big pot of hot water? What is going to happen to it? You think about that for a second. And what if I take the same kind of balloon and I put it into cold water? What would happen in cold water? You already know this, right? You already know this. In hot water, it's going to get bigger. It's going to get bigger. It's going to expand. And in cold water, it's going to get squashed. You knew this before you even met me. Remember? You knew that. Now, when both variables move in the same direction, when temperature goes up, the volume goes up. When temperature goes down, the volume goes down. When both of the variables go in the same direction, it's not inverse, right? This is inverse, pressure and volume. But when temperature and volume both get hot and big, or both get cold and small, when the temperature decreases, the volume decreases. This is called directly proportional. Directly proportional. And the graph is not curvilicious. It's one straight line. It doesn't have to go right at a 45-degree angle. As long as they're both going in the same direction. One can go faster than the other, but they both move in the same direction. So any straight line coming out of 0, 0 would be correct, right? But you don't want to make crazy. Just draw a line like that. Directly proportional. Now, I told you the story about taking my daughter to the mall and buying her a balloon and letting it go when it comes off and tying her. I told you that long story. All right, but you knew that when the balloon, when we go outside the mall, gets really, really cold, the temperature drops, the pressure drops, and the volume goes down, right? And then when we bring it back in the house and it gets hotter, the pressure increases, the volume gets bigger. And that's you don't have to hear that story again. This cartoon, though, really, really excites me because it's scary. It's a cute little cartoon. It's colorful. It looks like a cute little kid. But it's also really scary. Could you imagine if you held on to some helium balloons and there was enough of them, they could lift you off the ground? This is a nightmare. Think about what could happen. First of all, you go up in the air and then you get scared. You get about 10 feet off the ground. You get too afraid to let go because you're going to land. So you hold on and you keep going up. Oh my goodness. Could you imagine how scary this would be? Then in real life, the further off the ground you get, first of all, a plane could crash into you, which is probably not likely, but that would be scary. But the further up you go, colder and colder it gets, and your hands get more and more tired and cold, all of a sudden you're going to slip. Then you're going to fall a long way. Never do this. It looks like such a cute cartoon, but it gives me nightmares, this cartoon, right? All right, we're nearly done. We're going to draw 2 graphs. One is called, on the left, temperature as a function of volume. And on the right, we have volume as a function of temperature, sort of the opposite. Now, it's very important that you see this. There's even an asterisk at the bottom. The title and the axes labels must match for every graph, in every subject. Whatever word comes first, on the left side graph, temperature is a function of volume. Temperature comes first, that goes on the y-axis, volume goes on the bottom. Now, on the second graph, it says volume is a function of temperature. Volume goes on the y-axis, temperature on the bottom. Whatever word comes first goes on the y-axis. Don't mix that up, Now, you already know this. When the temperature goes up, the volume goes up because it's directly proportional. For the second graph, when the volume goes up, the temperature goes up. So both graphs are going to look exactly the same. Now, the slope's a little different. The one on the right looks exactly 45, and the one on the left is more of, what do they call it? Acute angle and is it obtuse? What do you call bigger? Holy cow, I'm having one of those little meltdowns. The small angle is acute, and the large angle is obtuse, I believe. Well, big angle, small. Doesn't matter. They both go in the same direction. They don't have to go exactly at the same rate. They could, like the graph on the right, I measured, I think, exactly 45, or tried to. The one on the left is definitely not at a 45, but that's okay. Temperature and volume are directly proportional. And when things are directly proportional, you get a straight line graph. Now, look at these three lines. These are all directly proportional. One's really sharp upwards, one really low upwards, and one's right in the middle. All the variables, whatever the y and x variables are, they go up and down together, directly proportional, not curvilicious like the pressure volume graph, not at all. And there is the end of this next slideshow. So we are good. The only thing I got to worry about is what happened in that little break, because now I got to go back in time and see it. I'm going to have to watch it myself. Hey, thanks for coming. Goodbye. See you another time. I'm going to do another Zoom in a